All right, so we're going to talk about chemistry and what chemistry is and how chemistry works and the basics of chemistry. I know we should be well far in advance of this right now, but this year seemed to go a lot faster than I expected it to. So today we're going to go through definitely this, and we're going to cover several more objectives. So the first one says define chemistry. Before I go any further than that, without looking down, without reading ahead, can someone just tell me in your own words how you would define chemistry if you had to write it down? Like, how would you define it? Anybody. I don't care. There's not a wrong answer here. Boom. Okay. Everything has to do with explosions, fire, or drugs, somehow, shape, form, or fashion. A combination of chemicals, mixing, pouring things together. Well, that's the thing. There is a Webster's Dictionary definition. We're going to talk about what it means. And when you read the definition, you're going to be like, wow, that I can understand that, but that's very encompassing. There's a lot that goes into it, and there is. And everything that's in the definition we're going to cover this year. So let's look at the definition of chemistry. So here's the definition. So chemistry is the study of the composition, structure, and properties of matter. The processes that the matter undergo, and the energy changes that accompany these processes. Okay? So when you read it, you're like, okay, I get that. That makes sense. But I want to take just a second, and I want to jump off into this really deep so we can actually understand what it means and what we're going to be looking at for the rest of the year. Okay, so chemistry is the study of. First of all, that means you're going to have to study. It's not something you can just absorb it like a sponge. You're actually going to have to put time and effort into it. So let's talk about the first word, composition. What does composition mean? What does composition mean? I like it, okay? So write this above this or right beside it. What, and you can write all over that. All those things you just got in your notes. What it's made of. So if I ask you what is the composition of water, what would you say? Be more specific. Try again. 2 hydrogens and 1 water. Do you agree that's the composition of water? That's what it's made of. Okay? Then you can talk about hydrogen. What is hydrogen made of? Okay? Protons, neutrons, electrons. Okay? Can you be specific with how many of them there are? We will get into that. We will talk about how we know how many of each are present. Okay? So that's the composition. You can also talk about the composition of oxygen, what it makes up oxygen. All right, number 2, the structure. What is structure? Okay, I like that. Okay, so let me change the color here. So how it's built and looks. Okay, we're going to get later on in this year. We're going to be talking about Lewis structures and what Lewis structures mean and what they are and how they work. And when you draw these things, so when I show you this little molecule right here that's in my hands. Why is it designed like this? How does it get its design? And what atoms make this shape and what the name of the shape is, what the bond angle of this thing is. It polar or non-polar? What type of intermolecular forces it have and what's its hybridization? We're going to talk about all of that. Okay? That is the structure. Does the composition affect the structure? Absolutely it does. Okay, so all of those things are going to play an integral part in this. Number 3, it says the properties of matter. There are 2 types of properties. What are the 2 types of properties? Physical and chemical properties. Okay, we're going to talk about that in this chapter. Do you think the composition, what it's made up of, affects its physical and chemical properties? Do you think how it's built, how it's designed, how it looks, affects its physical and chemical properties? Yes, absolutely. Are some metals better conductors of heat and electricity than others? Absolutely. And that is affecting how it's made and how it's built affects those things. Okay? There are some things that do other things better than others simply based on its composition and its structure. Okay? The processes that matter undergo. So just write this one word. How they change. Okay? What can we do to make them, force them, or recreate them? So what can we do under all of these circumstances of change? Because do you agree that things are constantly changing? All the time. And we're going to look at different ways things can change. And then finally, because this last part is the most important, if you take away this purple part, you lose humanity. You lose everything about life, because energy is the most important thing in all of life. If you have no energy, you have nothing. Okay? What is heat? It's energy. If you take away heat, what happens? Everything dies. Okay? You have to have energy in order for everything to work. So there's two ways that energy is utilized. First of all, can you create or destroy energy? No. Okay? So energy is either released or what? Or absorbed. That's it. You can either release it or you can absorb it. Okay? And we're going to talk about the different types of energy. What is it called when energy is moving? Kinetic. What is it when it's stored? Potential. What about what I would call heat energy? Thermal. What about electrons flowing? Electrical. Okay, we're going to talk about all those different kind of things. So now, let's reread this. Chemistry is a study of the composition, the structure, the properties of matter, and the processes that matter undergo, and the energy changes that accompany them. Does it make a little bit more sense now that you've kind of jumped off and see, we've got to talk about what it's made of, and then how it looks and how it's built, and then how do those things affect the physical and chemical properties, and then how do all those things change, and how can we make them change, and how can we force them change, and what do they do when they change, and what's going on with the energy when all those things occur. So it's important that we understand the basics of the word, because if we don't, we're not going to do a whole lot. So, a chemical. Whenever you hear the word chemical, most people associate with negative connotation, right? Chemical is bad. Stay away from chemicals. Don't touch chemicals. Don't eat. Don't drink. Don't do anything with chemicals. However, are all chemicals dangerous? No. Okay. If you have a highlighter, now would be a great time to get it out. Or if you just like to circle things, whatever, do me a favor and highlight or circle or star, underline, whatever, that part right there that's in red. Okay. Highlighters are going to be your best friend in this class. A chemical is any substance with a definite composition. What does it mean to be a definite composition? Very good. It never changes. Okay? Definite. It's always the same. You can't do anything with it, because if you change it, you change the entire chemical. So we've got three examples here. We've got sucrose, water, and carbon dioxide. Does anyone know what sucrose is in common name? Very good. Well done. Okay. It is sugar. Now, let's find the super nerds in here. Does anyone know the chemical formula for sucrose? What? It's not glucose. This is sucrose. Write that down. Okay, write that down. In biology, you should have heard at least something called monosaccharides, disaccharides, and polysaccharides. Okay? So what a saccharide is a complex starch or a sugar. Okay? What does mono mean? One. Okay, so it's one simple sugar. Disaccharides means two. So it's a combination of compounds that creates a little bit more complex. Okay? Sucrose is your disaccharide. What was your monosaccharide? Glucose. Okay, glucose was your monosaccharide. And your polysaccharides are your fructose and all that other syrupy stuff, right? So we're not going to get into this, but this is sucrose. So my question to you is, how is this a chemical? A chemical is defined as any substance that has a what? Definite composition. If you take one carbon out of this formula, is it sucrose any longer? If you take one hydrogen, no. If you take one oxygen, no. So definite means it will always be that. It can never be anything different to maintain that chemical identity. So that is what sucrose is. So as weird as it sounds, whenever we look at water, we know that is H2O. If you take one hydrogen off, or if you take the oxygen away, it's no longer that chemical composition. You can if you want to, but you don't have to write this down. But what if I change it to H2O2? What did I do chemically to that compound? I added what? One oxygen. Okay? And I completely changed this from water to hydrogen peroxide. Okay? H2O2 is hydrogen peroxide. The stuff in the brown bottle you poured on your boo-boos when you were little, right? That's what that stuff is composed of. Okay? Now, number 3, carbon dioxide. What's the chemical formula for that? CO2. We're going to get to a chapter about naming compounds, and you know how to name compounds. You just didn't know you knew. Okay, so look at the formula, and then look at the word, and where do you think the name comes from? Okay, there is a carbon, and then what about di? That means 2, and oxide means oxygen, so CO2. You didn't know you knew, but you do. You know how to name compounds, and we're going to get to that. I'm going to teach you how to do all that later. So that is what a chemical is. So when you hear the word chemical, don't be scared. It's something that is a definite composition. Now, are some chemicals dangerous? Absolutely. But for the most part, most things aren't that dangerous. Okay? So the branches of chemistry, I'm telling you now, you need to know all 6 of these. Organic chemistry. Again, here's where that highlighter is going to come into play. Please circle this word right here. Carbon. Okay? Organic chemistry, first of all, is the devil. Pray for you whenever you have to take it in college, if you ever have to. Why don't you take AP chemistry first, and then we'll see. Then you'll be ready for that. No, you don't want to do that. I can assure you, you don't want to do that. You can't. You don't need to take organic before you take inorganic, which is AP Chem, because yes, most definitely. Okay. So organic chemistry study of carbon-containing compounds. So do me a favor, out beside this, write the word, and I apologize, it's written like that, but oh well. Living. Okay. If you are on this planet and it is alive, and I'm not talking about humans and animals, I'm talking about plants, anything, microorganisms, all of these things are living. They must be a carbon-based component. Okay. So the reason that carbon is so special, and it has its own entire branch of chemistry devoted to it, has something to do with its structure, has something to do with how it's designed and built. I'm going to throw some curveballs at you. Let's see how many of you actually retain information from 8th grade. There's these rings that go around atoms, right, that electrons sit on. Okay? All right, so your electron cloud, if you will. We're going to kind of talk about the depths of that later on. Does anyone remember how many electrons can fit on that first ring? 2, very good. And everything after that can hold 8. Now, this is an important question. We know carbon wants to have 8. However, does anyone know how many carbon has? In its outer, what's the outer ring called? The valence electrons, right? Okay. It has 4. Think about this. It needs 8, but it's got 4. So what does it do? Does it gain 4 more, or does it lose those 4? That's why it's special. That's the reason why carbon is so special, is that it has the ability to do both. Does that make sense? Logically, so okay, you can either lose 4 or gain 4. And that's what the reason carbon has its own branch, because it can do so many different things. Are any of you sci-fi people, like you love the sci-fi world? Anybody? Okay. Some of you may have heard of this. If you haven't, if you ever watched, one of the things they're trying to figure out is if other universes, other planets, way, way, way far away from here, actually have things called silicon-based life forms. You may have heard that term before, which means things that are living have silicon base instead of carbon base. Can you look up there and tell me why they think that's a possibility? Where's silicon? It's right underneath carbon. Okay, so they think that there's a possibility that there are ways that silicon can do the same thing carbon does and have living forms. Again, they're trying to prove all that. Who knows if that's actually true or not. The one last thing I want you to write beside organic chemistry, there's one exception. There's one exception, and that's CO2. CO2, is it carbon containing? Yes, but it does not fall under organic. It actually follows under inorganic. Okay, and inorganic is this class. We're going to study most things that do not have carbon. Now, we're going to talk about stuff with carbon in it, absolutely. Okay, but for the most part, we're going to study the non-organic substances, many of which have organic fragments bonded to metals, again, which we'll talk about later. All right, so number 3, P-Chem, or physical chemistry, is the study of properties and the changes of matter and their relation to energy. So how physically exists in the real world. What does it do physically? How can we manipulate it and manage it physically? And then also the energy. Number 4 is analytical chemistry, or AChem. Okay, what do you do when you analyze something? Okay, or in our words, if you want to highlight, we are trying to identify something. When we look at a species, or we look at a compound or something, we're trying to figure out what it is, what it looks like, how it works. We are analyzing it for the whole entire substance. Okay, so the components and the composition. So that's AChem, analytical. Bio, what does bio mean? So we are studying the living chemistry. What? Anybody want to be a pharmacist? Okay, if you do, this is your life right here. Everything you do revolves around that science, because when you take a medicine, is it a chemical? Are you putting it into a biological system? The chemicals within the medicine affect your biological system. We need to know how they affect us. Is it a positive thing? Is it a negative thing? Have you ever heard those commercials for the drugs? They give you, this relieves your headache, but it gives you 10 million other issues. Constipation, diarrhea, which we think, wait a minute, how do you have both of those? That doesn't make sense. Okay? Death. You can die if you take a headache medicine. It's crazy. I saw something. It was a Super Bowl commercial one time. It was a 30-second Super Bowl commercial. 7 of the 30 seconds were talking about the positives of the drug. The rest of it were the negatives. Like, you got 7 seconds to tell me how it's good, but the rest of it tell me how I'm going to die? That's not good marketing. Okay? So again, this is biochemistry. And then finally, theoretical chemistry. Anybody like Big Bang Theory? Okay. Sheldon Cooper is a theoretical physicist. Same kind of stuff, but on the opposite end. We're looking on the micro scale, or then really the pico scale. We're talking about how the theoretical chemistry works. You know, they're always trying to figure out how to make things better, smaller, more efficient, faster. So using mathematics and computers to understand the principles behind observed chemical behavior to design and predict the properties of new compounds. So highlight that last little phrase right there. Some of you may know this. As a matter of fact, if you guys will look on that periodic table over there on that wall, do you see how on the bottom, okay, there's the 2 little bottom rows that are kind of pulled out and extracted, but the one right above it, there's some empty boxes towards the bottom right. This past year, they have officially and finally finished the periodic table. It's completely full. We've got 118 elements. Okay, I've actually thought about buying a new one, but they're really expensive, so I haven't had a chance to do it. Okay, I may print it out and put it up there. So the cool part is that they finally finished it, and there's 118. And every time people ask that, what are they going to do when they get to 119? Okay, and again, it's a question, but what are we going to do? But they finished all of that, and the reason they found all that was due to theoretical chemistry. They figured out a way to make those things happen. None of them are man-made. None of them are natural. They have to be created in a lab. Okay. All right, so 2 basic types of research. The first research is basic. Okay, do me a favor, you definitely need to know this. Basic research is simply used to increase your knowledge. That's why we do it. Okay, that's the only reason we do basic research, is to make us a little bit smarter. Okay, so how and why a specific reaction occurs, what the properties of a substance are, and then things such as like discovery of Teflon. It was something to increase our knowledge. I know what you're thinking, what is Teflon? Does anyone know what Teflon is? A song? And this, I can make sense. I can understand that. Any of y'all bake cookies? You know, on the instruction it says, do not use a non-stick grease thing, okay? Because that surface is non-stick. The chemical that makes cooking surfaces non-stick is Teflon. It doesn't stick to it, okay? That is what Teflon is, okay? All right. So if you go home and you look up like your pots and pans, it may say the word Teflon on it, because that's the chemical that allows it to be non-stick. Finally, applied research is something to solve a problem. Okay, so one of the problems that we have right now in this world is cancer. Okay, it's a really big problem, and we're trying to do applied research to figure out ways to solve the cancer issue. We can talk about AIDS. We can talk about HIV. We can talk about all these genetic formations. The Zika virus is really big right now. What are we doing to try to create something to solve a problem? Because those are things. Right here real quick, development of new refrigerants. Refrigerants are things that keep other stuff cold. And this was one of the issues a long, long time ago. If any of you ever take environmental chemistry, you'll learn about CFCs. Okay? You don't have to write. I do want you to write CFCs, but you don't have to write what it stands for. A CFC stands for what? Chlorofluorocarbon. And what they figured out about chlorofluorocarbons was that whenever they were emitted from old refrigerator type things, that it actually destroys the ozone layer. And so they had to find a new chemical, a new refrigerant that they could put into these machines that allowed them to not affect the atmosphere as much. Okay, so that's what CFCs are, chlorofluorocarbons. Okay. All right, so what does this stuff lead to? Whenever we discover these things, we have technological developments that improve our quality of life. Computers was a major improvement of the quality of life over the past several years. The phone sitting on your desk is a mini computer. Think about where it came from. The amount of storage that's in probably 1/1000th of your phone used to take up a room this big. Okay, I mean just massive, massive, massive rooms to have all this data storage that now you can put on something this tip is the big of this pen. It's amazing how technology has improved over the past years. Catalytic converters. Does anyone know what a catalytic converter is? It is in cars? Go ahead. Okay. Okay, it's in your exhaust system. So what happens is whenever your car, your combustion engine vehicle, produces its byproduct, which is dangerous stuff. Instead of blowing all that dangerous stuff out into the atmosphere for us to breathe, the catalytic converter is in your exhaust system. What happens is kind of like a spongy metal, and when the gas goes, or excuse me, when the fumes go through it, it's charged, and those fumes stick to the catalytic converter and does not allow it to come out of the back end of your vehicle. So it's actually a safer environment for us, and it's not as dangerous for us to breathe. So it's like when you see China and Japan, and they're constantly in smog. You know what smog is, right? Smoky fog. Okay, that we're protecting ourselves from issues like that over here because of our EPA environmental standards. Okay, biodegradable materials. What is that? They break down naturally, so life naturally breaks them down over time. So this is a big issue in our landfills. The more stuff we put in there that's non-biodegradable, the more we have to deal with it. Okay, and then finally we talk about phones. And then basic research, applied research, and technological development often overlap. One of the big things that I kind of talk about at this point, but is how we can improve. Fuel efficiency is a really big deal. Thank you. How many? Perfect, even better. Okay. How we can improve the fuel efficiency, how can we improve the environmental standards, like do we want to continue using gas-powered cars, or do we want to go to electric, and what are some other options available for us to improve our cars? Personally, I think one of the things I wish we would go to is hydrogen-powered cars, because the byproduct of hydrogen is water, which is nice to have in the air, and it also can produce a little bit of oxygen. If you're putting oxygen out in the back of your vehicle, that's just helping the environment out. Okay? So it's kind of an interesting concept to think about of how we can change and manipulate all that. Okay? So the 8 top chemicals made in the United States, again, you don't need to know any of these things, but we will talk about more in depth of what it is. One of the craziest parts to me, let's make sure I'm saying this right because it's been a while since I've looked at it. I'm not going to spend time with that. So sulfuric acid, ethene, propylene, ammonia, chlorine, phosphoric acid, sodium hydroxide, and 1,2-dichloroethane. There's just a lot of things that you can do with a lot of those chemicals. Okay. All right. So section 2. This is actually getting into chemistry. And some of the stuff we talked about, but I want to get into the depth of it. So matter is anything that has mass and takes up space. Do me a favor. Add this word right here for me. Does anyone know the "and" part, the last word about matter? Starts with an I. It's a physics word. Very good. Inertia. Okay, does anyone know what inertia is? There's a law that kind of goes with it. An object in motion tends to stay in motion unless enacted upon by an outside force. Now, so what that means is if I hit a golf ball, it's in motion. Why does it not stay in motion? Gravity, very good. So if we go into an environment where there is no gravity, there is no. Now think about this. What if I could take the gravity off of this planet and I hit a golf ball? would it still eventually slow down? What's causing it? What about the air? Friction. Okay, so friction actually slows stuff down. So if you could hit a golf ball in a room with no air, with nothing, it will go and go and go and go and never stop. Okay, so it's kind of an interesting to think, which is space essentially. Mass is the measurement of the amount of matter. It will never change. And again, how is it different from weight? What is weight? It's the force of gravity. So if you go from here to the moon, does your weight change? But your mass does not. Very good. Volume is the amount of three-dimensional space an object takes up. We've already talked about that significantly. The building blocks of matter. These are important. Make sure you put a side by side all three of those. And every year people get confused. What is an atom and what is an element? What's the difference between those two things? Okay. An atom is a singular thing. Okay. An element is a group of the exact same atoms. Okay, so if I say that is an element of carbon, you're talking about more than one atom. Okay, so an atom is a specific thing. So it says it's the smallest unit of an element that maintains the chemical identity. And do me a favor, underneath right here where it says chemical identity, we're talking about three things. What are the three properties of an atom that must be present? Protons, neutrons, and electrons. Does every atom, and when I say every, I mean all umpteen bajillion of them, have the same number of protons, neutrons, and electrons? No. Okay? Which one of those tells you what the element it is? The number of protons tells you which element it is. Okay? Up there, all those numbers that they're in order of, 1, 2, all the way to 118, that is the atomic number. The atomic number tells you the number of what? Protons. Okay, and we'll get into that a little bit later on. All right, next, an element. An element is a pure substance that cannot be broken down into simpler, stable substances and is made up of one type of atom. So if I had in my hand nothing but diamond, just a hunk of diamond, what is the only atom in there? You know what diamond's made out of? Carbon. Atom. Carbon atoms. Okay? Coal is also carbon, so it's graphite. It's just different ways of putting it together. So that's what an element is. It's a compound that cannot be broken down any less. Now, what is a compound? A compound is a substance that can be broken down into simple substances. Each compound is made up, and this is where you need to highlight, of two or more elements that are chemically bonded. That's the key. Okay, two or more different elements that are chemically bonded. Okay, do me a favor. Underneath all that, where it says bonded, there should be enough space to write this. Anybody know how many bond types there are? Try again. 3. Okay. Does anyone know your 3 bond types? Okay. Write those down. Covalent, ionic, and metallic. These 3 words must become very, very useful in your vocabulary because they are going to be here forever. We're going to talk about these the rest of the year. Okay, and being able to identify if it is a covalent compound, an ionic compound, or metallic compound is going to be very vital to your success. So these are the 3. Go ahead and start thinking about those, getting them ingrained, and we'll talk about the differences later on. Okay. All right, so this is a picture of an atom, true or false? It's a trick question. You cannot have a picture of an atom. So it's just kind of what it's thought to look like. And it kind of looks like a planet, so it's not even real. Okay? All right? So this is a different way of building blocks of matter. So let me ask you something. All these green things represent what? Atoms. What do all those sticky line things represent? So do me a favor. Right there, we're going to call that a bond. Okay? So, is that not on there? That's fine. I deleted it off there, so don't worry about it. So let's just talk about it up here. Some of the pictures I took off. So carbon atom, and then they are bonded together. Is this one or more different types of atoms? It's just one type, right? So this is an element. Okay, because it's the same atoms grouped together. Now, over there, we have oxygen, we've got carbon, and we've got hydrogen. Is that more than one type of element? Yes, so this is can y'all read that? There, it says the compound. I honestly don't know. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That is sucrose. That is a picture of sucrose. Okay? Because you have 12, you've got 12 carbons, 11 oxygens, and 22 hydrogens. You just can't count them all because you can't see them all. Okay? It's a representation. Okay? Now, these two words are going to be very important to us over the year as well. So please, please, please stick these in there somewhere. So I would circle this slide, and I think, let me make sure. I would circle both of these two slides right here. The entire slide. Okay. The next one, extensive and intensive. Is it the bottom two? Perfect. Okay, so I would know these bottom two. So extensive and intensive properties. Extensive, this is how it's defined, depends on the amount of matter. Extensive depends on the amount of matter. And then it gives you 3 examples. It says volume, mass, the amount of energy a substance has. Volume, mass, the amount of energy. So let me give you an example. If I take a cup and I pour some water in it, does that water have a specific volume? Does it have a specific amount of matter in that cup? Let's just be more specific. Does it have a specific number of water molecules in there? If I take more water and I pour it in there, 2 questions. Did the volume go up or down? It went up. And did the amount of water molecules go up or down? It also went up. So, did the amount of water, the matter, change the volume? That is an extensive property, right? If you are eating a cheeseburger, is there a specific amount of matter in that cheeseburger? If I take a piece of your cheeseburger and rip it off, did I change the amount of matter? Did I change the mass of that cheeseburger? Yes. So does it matter how much matter you have? Yes. If I take or add, it changes your amount. I'll give you another one. If you have just a little bit of gasoline or a gas station and both of them blow up, is the amount of energy going to be drastically different? Yes. So the amount of stuff that you have, does it affect your quantity or your value? Yes. Let me give you another example that's more real world. If you went in to buy a shirt, okay, does the amount of money that shirt costs determine if you're going to buy it or not? Absolutely it does. You can go in, if it's $10, sure. If it's something nice. But if it's $300, you're probably not, hopefully you wouldn't buy that shirt. Okay? So the point is the amount of money matters. So in a weird way, extensive, the matter matters. That is for extensive. So what does that have to do with money? If it's expensive, does it matter? Yes. Okay. So extensive matters. Expensive matters as well. So what about those things that it doesn't matter if you have a lot of it or a little, it's always going to be the same. Okay? That is what is called intensive properties. So again, if it's intensive, it doesn't matter how much you have. You can have a little or a lot, and it's always going to be the same. You already know one of these. You've done a simulation on it. No matter how big or small that block was, what never changed? That is one of them. Okay, so let's look at some of the others. Melting point, boiling point, ability to conduct electricity, or the ability to transfer energy as heat. If you have a small pot of water or a big pot, does it still heat up the same way? Yeah. Okay, it doesn't matter how big or small your pot is. Do the smaller pots have less stuff? Have less matter, right? It's a smaller pot, but it still heats up the same way. If you have a really big wire or a really small wire, does it change the way the electricity goes through? Are you still going to get shocked if you stick it in an electrical socket? Yeah, you're still going to get hurt. Okay, it doesn't matter how big that wire is. Okay, the other two. We've already defined these two things before, but I want to kind of say them again just to make our brains kind of connect it. Melting and boiling point. It is not a point. A point is what? It's the temperature at which, okay, and then we can continue on. What is the melting? What happens in melting? So we're going from a solid to a liquid. So it's the temperature at which a solid goes to a liquid. And what is a boiling? A liquid to a gas. So those are the two differences in your melting point and boiling point. But let me ask you, if you have just a little bit of water, if you have a lot of water, is the temperature the exact same? What's the boiling point of water? In Celsius. Have they ever said, oh, if it's only a gallon, it's 35 degrees Celsius, but if you have a whole lot of it, it's 100 degrees. What's the boiling point of all water, no matter how much you have? 100 degrees. Okay? Does that make sense? So you can have a little water or a lot of water. Will the boiling point always be the same? Yes. That makes it an intensive property. So again, the amount of matter does not matter. The only way for you to remember this is you to actually physically spend time looking at it. I can't get it into your skull any better. You actually have to physically do it yourself. Okay? So let's look at some properties. And again, we talked about how it looks, what its composition is, and some of the chemical properties and physical properties. So, properties of matter. Some of them are electrical conductivity. Do y'all have this sheet? That's fine. Okay. What is electrical conductivity? The ability to carry electricity. If you have the ability, write this in. The ability to carry electricity is nothing more than the flow, what is E minus? Of electrons. Okay? Copper is a good electrical conductor, so it's used in a lot of wiring components. Some other things is heat conductivity. Okay? So it's a way for thermal energy to be transferred back and forth. We know what density is. It's mass over volume. So it's the amount of how tightly matter is packed in. Okay? In terms of a student relationship, how could I increase the density in this room? Add more students. Did I change how big this room got? No, this is concrete walls. I can't change it. So the more students I put in here, does my density go up or down? It goes up. Do I have more things packed in the same amount of space? Okay? Because if this room was on a scale, every student that came in, what would happen to the mass of the room? It'd go up. The volume doesn't change. How would I decrease the density in this room? Take students out. Every student that left, does the mass go down? Yes, but the volume never changes. So that's what density is. Okay. Melting point, we know that. Boiling point, we know that. This is a weird one. Actually, these last three. Index of refraction. Does anyone know what refraction has anything to do? Bending of light. Very good. So, have you ever seen how, like, if you're standing in a certain, like if a sprinkler's going off, you can see the rainbow go through it? That's because when the sunlight passes through it, it breaks it off into its things. And we're going to talk a lot about that. We're going to get into malleability later, so I'm going to hold off on that. And then ductility. We'll talk about that. You'll actually have to write that down. Okay? All right, so we know that there are two types of properties that we're going to be talking about. We're going to talk about physical properties and chemical properties. Now, physical properties and physical changes are kind of one and the same, and then you have chemical properties and chemical changes that work together as well. So here's what a physical property is. It's a characteristic that can be observed or measured, and this is the most important part, without changing the identity of the substance. A physical property can be observed even if you do something to it, it's still the same stuff. And this is the number one thing that students miss every year. Is boiling water a physical change or a chemical change? Why is it physical? It's still water. What have we done to it? You boiled it. What did it go from and to? Is it still water? So do me a favor, write this down. Okay? If we change, come on, pen, change the state of matter. Now, what are the three major states of matter? So solids, liquids, and what? Don't talk about plasma. I don't care about plasma. Okay? So again, if you melt ice, what does it melt into? What did it start as? Don't say ice. It started as water, right? It's just in the solid state of matter. So it's still water no matter what. But the problem is students say, I have this liquid stuff I can hold, and it disappeared. That's the problem. It doesn't exist anymore. How is it still water? It's just a gas. You've separated it to the point you can't see it anymore. It's still floating around, right? Okay. What happens if it begins to boil and you hold a lid above it? What does all that boiling do? It condenses on the glass. It's still there. You just can't see it. So physical change is a change in a substance that does not involve a change in the identity of a substance. So no matter what you do to it, it's still the same. So if I grind pepper, is it still pepper? What have you done to it? You just made it smaller, right? What about cutting? If she cut this sheet into these things, is it still the sheet? It's just a smaller piece of the sheet, okay? What happens, again, we talked about melting and boiling. So are there any other things you can think of that are actions that you can do to something and it does not change it? Anybody got anything? Yeah. Okay. If I take something and I smash it into 100 pieces, is it still whatever you smashed? Yeah, if you break glass, it's still glass. It's just smaller. Okay. So we're going to get there. So if we do all these things to everything, what is a chemical change then? What makes something chemically changed? You have to make it completely different from the beginning. So if I take a piece of wood and I burn it, is it wood anymore? No. Okay, it's completely different. I always get everyone on this. What about frying an egg? It's a fried egg. But did you change anything chemically? I'll tell you tomorrow.